Uh, at the end of the previous lecture, we began to discuss inductive limits of C-star algebras. So let's recall, first of all, let's recall the general category theoretic definition of an inductive limit. So we work so far in an arbitrary category A, and we take a directed partially ordered set I. And by definition, an inductive system in A, indexed by I, is a family of objects together with morphisms phi ij, which are defined whenever I is less than or equal to j. And these morphisms are, so they satisfy the natural compatibility condition, meaning that if we have three indices I, j, and k, then two possible ways of getting from I to k are the same. So we may first apply phi ij and phi jk, or we can apply just phi ik and the result will be the same. So briefly, this is just a functor from I to A if we make I into a category in a natural way. So now if we have an inductive system in our category, then we define an inductive cone over our system to be an object of the same category together with a family of morphisms phi I from AI to A, such that for whenever I is less than or equal to j, this diagram commutes. Next we define morphisms between inductive cones in a natural way. Namely, if we have two inductive cones, A and B, over the same inductive system AI, then a morphism from this cone to this cone is just a morphism from A to B, such that this diagram commutes for every I. This is a morphism of inductive cones. So the class of all inductive cones together with their morphisms forms a category, and by definition an inductive limit of our system is just an initial object of this category. And it is denoted like this, or more explicitly like this. So explicitly this means that this is an inductive cone over our system, such that for any other inductive cone there is a unique morphism from A to B, such that this diagram commutes for every I. This is the inductive limit. So this definition defines an inductive limit in terms of the respective universal property. So of course, this definition doesn't imply that the inductive limit exists. And actually, we have seen that there are some examples, some natural examples, where the inductive limit doesn't exist. For example, if we take the category of all Banach spaces and bounded linear operators as morphisms, then in general, this category doesn't have inductive limits. Also, we considered, at the end of the lecture, we considered an important special case of inductive systems and inductive limits. Namely, we discussed directed chains of sub-objects. So namely, we considered either the category of sets, or the category of or groups, or abelian groups, or modules over any ring, or the category of rings, or the category of algebras, or the category of star algebras. In all these cases, the situation is the same. So, namely, we take an object of our category, and suppose we have a chain of sub-objects indexed by our poset I, such that the inclusions between them are compatible with the order relation on I. So we get a directed chain of sub-objects of A, and clearly they form an inductive system. So the maps phi ij are just the inclusion maps. So a simple exercise in this case that in such a situation the inductive limit exists and is equal to the union of these sub-objects. So this works actually in any of these categories. And another important case where a similar situation holds, namely this is the case where A is the category of C-star algebras. Again, we assume that we have a C-star algebra A and the family of closed star subalgebras of A, which are included into each other in a compatible way with the order relation on I. Again, in this case, a simple exercise is to show that the inductive limit also exists and is equal to the closure of the union of this chain. In general, we have to take the closure because in general this union is not necessarily a C-star algebra, a C-star subalgebra. But modulo the closure, the construction is very similar to this case. An important point here in the proof of this exercise is that all star homomorphisms between C-star algebras are contractive. They don't increase the norm, and this is very essential. Actually, we can do the same procedure in the category of, for example, of Banach spaces and contractive linear maps. And the situation will be the same. We always have such an inductive limit, and it is equal to the closure of the directed union of our chain. But if we consider, again, if we consider Banach spaces and all bounded linear maps, then in general, such a chain doesn't have an inductive limit. Let's now introduce morphisms between inductive systems. Morphisms are defined in a rather straightforward way. Namely, if you have two inductive systems, say AI and BI, inductive systems in any category over the same directed set I. Then we define a morphism from the first system to the second system. So briefly, this is just a natural transformation of the respective functors. It's a natural transformation of the respective functors. So if we look at inductive system as a functor from I to A, then the morphism is a natural transformation, and explicitly this means that we have a family of morphisms Fi from AI to Bi, which are compatible with the connecting maps in our inductive systems. That is the following diagram. Here we have two indices, I and J, and I is less than or equal to J. Then we have here the connecting map phi ij, and here the connecting map psi ij, here Fi, and here Fj. So this diagram has to be commutative for every I and J. Such that I is less than or equal to J. The class of all inductive systems over I becomes a category. Actually, this is the category of functors. category of functors from I to A, the category of inductive systems over I. And if we assume that every inductive system indexed by I has an inductive limit, then it's a simple exercise to show that the inductive limit becomes a functor from this category to the category A. So if every inductive system over I has an inductive limit in A, then the inductive limit becomes a functor from the category of inductive systems to A. So the exercise is first of all to define this functor on morphisms, not only on objects but also on morphisms, and to explain that it is indeed a functor. Okay, let's now proceed to an explicit construction of an inductive limit in any of these categories. So our next goal is to show that any inductive system in any of these categories has an inductive limit. Let's start with the case where A is the category of sets. Actually, we will see shortly that basically every category from this list somehow reduces to the category of sets. So we take an inductive system, AI, phi ij, inductive system of sets. We form this joint union of our family of objects, and we define an equivalence relation on this joint union as follows. If we have two elements of this joint union, say one of them sits in AI and another AJ sits in AJ, so they are two elements of this joint union, we say that they are equivalent by definition if there exists an index k, which is greater than or equal to I and greater than or equal to j, such that the images of these two elements in the set AK are the same. Phi ik of AI equals phi jk of AJ. So the picture is as follows. This is AI, this is AJ. They sit in two different sets, AI and AJ. By the way, in general, I and J are not necessarily comparable. But if we take K, which is big enough, then the images of these two elements will be the same elements of AK. So this is our equivalence relation. A simple exercise is to show that this is indeed an equivalence relation. That is to prove the transitivity in particular. And second, it's easy to observe that this is the smallest equivalence relation on this joint union, such that every element AI of the set AI is equivalent to all of its images in AJ for all j greater than or equal to I. So these elements are equivalent for every EI and in EI, and for every j greater than or equal to I. So clearly these two elements are equivalent because we can let this is immediate from this definition. So AI is equivalent to this element. In this case, these two are the same. This will be the identity map. So every element is equivalent to all of its images, and this is the smallest equivalence relation satisfying this condition. Okay, so let's now consider the quotient of the disjoint union modulo this relation, as denoted just simply by A. And we have natural maps from AI to A for every I. Namely, first we embed AI into the disjoint union. And then we take the quotient map to A. If we compose them, then we get a certain map phi I from AI to A. And it's easy to observe from this property that A becomes an inductive cone over A. This is immediate from this equivalence. But actually we can say more. This is not just an inductive cone. This is an inductive limit of the respective system. A together with the morphisms phi I is an inductive limit of our inductive system in the category of sets. By the way, let's observe that this construction is actually connected to our special case where we considered directed chains. And the relation is given by the following picture. So first of all, we observe that if I is less than or equal to j, then the image of AI in A is contained in the image of AJ in A. Simply because A is an inductive cone. This is because of the following relation: phi I equals phi j composed with phi ij. So the image of this map is contained in the image of this map. So we can now consider the following picture. This is AI, and this is AJ. This is phi ij. Here we have their images in A. Here we have just the inclusion map, phi I and phi j. So we see that we have a morphism of our inductive system into the respective directed chain of subsets of A. And because of this exercise, the inductive limits are actually the same. So the inductive limit of AI is the same as the inductive limit of phi I of AI. And this is just A, because A is just the union of the respective subsets. Of course, I don't claim that this morphism of inductive systems is an isomorphism. So we have an isomorphism between their inductive limits, but the system themselves are not necessarily isomorphic. But on the other hand, if all the connected maps are injective, and this is our second observation, if all the maps phi ij are injective, then let's observe that all the maps phi I are also injective. Well, indeed, just look here. If I equals j, then such elements, if I equals j, then they sit in the same sets, in the same set AI, and such elements can never be equivalent unless they are equal, because this arrow is injective. So two different elements of the same AI are not equivalent, and so phi I is injective. So in this case, if we now look again at this picture, we say that we have an isomorphism of our inductive systems. So not only the limits are isomorphic, but also the inductive systems are also isomorphic. And our original inductive system is isomorphic to the respective directed chain, together with the inclusion maps. So they are isomorphic as inductive systems. So in summary, every injective inductive system of sets is isomorphic to a suitable directed chain of subsets. Okay, so this is the construction of the inductive limit in the category of sets. Let's now take any of the following categories. For example, the category of abelian groups, or the category of rings, or the category of algebras over any commutative ring, or the category of star algebras over the complex numbers. So we take an inductive system, AI phi ij, an inductive system in our category, and we form the inductive limit in the category of sets. Take the inductive limit in the category of sets that we've just constructed. And here is a rather straightforward exercise. First of all, we can make A into an abelian group. We define an abelian group structure on A as follows. If we take two elements of A, so they are equivalence classes of elements of respective groups, AI and AJ. So if AI sits in AI and AJ sits in AJ, then choose any element K which is greater than or equal to I and J simultaneously, and let the sum of the respective elements of the inductive limit, that is, of the equivalence classes of these two elements, be equal to the sum, the equivalence class of their the sum of their images in AK. So the exercise is to show that this is well defined. This operation is well defined. First of all, we have to show that the right-hand side doesn't depend on the choice of K. And second, show that the result doesn't depend on the choice of representatives in the respective equivalence classes. So it is well defined and makes A into an abelian group. So the inductive limit of our system taken in sets becomes an abelian group. And I claim that this abelian group is nothing but the inductive limit of our system, but now in the category of abelian groups. What happens if we take, for example, the category of rings? Here the situation is more or less the same. We can now define, so if A is the category of rings, we can define multiplication on A in a similar way. So A becomes a ring under the following multiplication. So again, we take two elements, choose k as shown here, and define the product of the respective elements of A in the following way. AI and J. So it becomes a ring, and again, it is to show that this ring is the inductive limit of our system, but now in the category of rings. In the category of rings. And we have more or less the same picture in the category of algebras and in the category of star algebras. So if A is the category of K algebras or the category of star algebras, so then the simple exercise is to define a K algebra structure, respectively a star algebra structure, on A, and show that A is an inductive limit of our system in the category A. So the construction is absolutely the same. So, for example, to define involution on A, where in the case where we work with star algebras, to define involution, we take an element of A, choose a representative, and apply the involution to this representative, and then take again the equivalence class. And this is well defined and makes A into a star algebra. Okay, so in summary, in any of these categories, the inductive limit, so the underlying set of the inductive limit is just the inductive limit in the category of sets equipped with suitable algebraic operations. What happens if we work in the category of sister algebras? This is the category we are mostly interested in. So now let A be the category of sister algebras. In this case, this construction has to be slightly modified as follows. So we take an inductive system, AI, phi ij, inductive system of sister algebras. And first of all, we form the inductive limit in the category of star algebras, as shown here. Let's denote this inductive limit as denoted by A0, for example. In the category of star algebras. And the respective canonical maps will be denoted by phi I0 from AI to A0. Canonical homomorphisms, which appear in the definition of the inductive limit. So in general, A0 is not a sister algebra, but we can modify it to make it into a sister algebra in the following way. First of all, we define a seminorm. We define a seminorm on A0 as follows. If AI is an element of AI, we define our seminorm on the respective equivalence class of this element to be the infimum of the norms of all images of this element under the maps phi ij over all I greater than or equal, over all j greater than or equal to I. So a simple exercise to show that this is well defined, and moreover, this is a C-star seminorm. This is a well defined C-star seminorm. on A0. And moreover, we can actually replace the infimum bound by the limit here. And this is quite easy because we know that all the maps phi ij are contractive. So the respective net, which appears here, is decreasing, is non-increasing. So the infimum is equal to the limit of this net. Okay, the next step is to make this A0 into a pre-sister algebra. So we simply quotient out the ideal where this seminorm vanishes. So let n denote the set of those elements in A0 for which this seminorm vanishes. So since this is a C-star seminorm, it follows that n is a two-sided star ideal. N is a two-sided star ideal of A0. In particular, the submultiplicativity of the norm implies that this is a two-sided ideal. If the norm of A, if the seminorm of A is 0, then the seminorm of AB for every B is also 0, and the seminorm of BA is also 0. So this is a two-sided ideal, and actually this is a two-sided star ideal. This implies that if we quotient out this ideal, then the quotient becomes a pre-C-star algebra. That is a star algebra equipped with a C-star norm with respect to the following C-star norm. So it's easy to see that this is well defined and doesn't depend on the choice of the representative and determines a C-star norm on the quotient. Let's now take the completion of this pre-C-star algebra. Let A denote the completion of this algebra. So A is a C-star algebra. A is a C-star algebra. Observe now that we have canonical maps from AI to A for every I, which are constructed as follows. So first of all, AI is mapped to A0 by means of phi I0 of this map. So we compose this with the quotient map. The quotient map. And finally, we embed this into A, into the completion. So the composition of all these maps will be denoted by phi I. And clearly, this is a star homomorphism. And now, a simple exercise is to show that A, together with these morphisms, is an inductive limit. An inductive limit of our system in the category of C-star algebras. So we see that in the category of C-star algebras, any inductive system has an inductive limit. Again, just like in the case of sets, we have a natural morphism from our original inductive system to a suitable chain of C-star subalgebras of A. So as before, if I is less than or equal to J, then phi I of AI is contained in phi J of AJ. By the way, both of them are C-star subalgebras of A. Let's recall that the image of any homomorphism between C-star algebras is automatically closed. This was discussed some time ago when we discussed quotients of C-star algebras. So the image is automatically closed, and they become C-star subalgebras of A. And we have the following commutative diagram. AI, AJ, this is phi ij. And here we have these two C-star subalgebras of A. Phi I, phi j, and here the inclusion map. Also, it's clear from the construction that A, our C-star algebra, well, in general, it is not the directed union of our chain, but it is the closure of the directed union. A is the closure of this directed union. We must take the closure because here we take the completion. So in general, this subalgebra is dense in here. So we must take the completion and we get this equality. And this is nothing but the inductive limit of the respective chain of C-star subalgebras. So we see that just like in the case of sets, we have a morphism from this inductive system to this inductive system, and their inductive limits are isomorphic. And again, if all the connecting maps phi ij are injective, then it's easily seen that the inductive systems themselves are isomorphic. If all phi ij are injective, and let's recall that the injective maps between C-star algebras are automatically isometric. Then all phi I are also isometric. And this is more or less immediate from this formula. So if we look here, we see that all these numbers are the same. So there is no need to take the infimum. All of them are the same. And so the norm of, the semi-norm of this equivalence class is equal to the norm of AI. And so phi I is an isometry. In particular, we see that n is 0 in this case. This semi-norm is actually a norm. Is 0. And so these two inductive systems, this one and this one, are isomorphic. They are isomorphic. So in summary, an inductive system of C-star algebras is isomorphic to a suitable directed chain of C-star subalgebras of a C-star algebra. We will often we will often work with inductive limits of in two categories, namely in the category of C-star algebras, in the category of abelian groups. So in general, the inductive limits in these two categories are not the same. So the underlying sets and the underlying abelian groups are not the same. So in order to distinguish between these two types of inductive limits, we will sometimes use the following extended notation, namely the inductive limit in the category, for example, of abelian groups will be sometimes denoted like this. This is the inductive limit in the category of abelian groups, or in the category of rings, or in the category of star algebras. And the inductive limit in the category of C-star algebras will sometimes be denoted like this. This is the inductive limit in the category of C-star algebras. Let's look now at some concrete examples of C-star inductive limits. Example exercise 1. Let's consider the following standard directed chain of algebras, which we have already considered many times in our course. So we consider algebras of square complex n by n matrices and embed into every mn into mn plus 1 in the following standard way. So every matrix A goes to A plus 0. So clearly this is injective star homomorphism. So this becomes a directed chain of algebras, and clearly it's clear from the above examples that let's observe that the algebraic inductive limit of this chain is just the algebra M infinity of infinite matrices such that all but finitely many entries are 0. On the other hand, all these algebras are C-star algebras. So what if we take the inductive limit in the category of C-star algebras? So the exercise is to show that the C-star inductive limit of this chain, of this sequence, Mn, is isomorphic to the algebra of compact operators, script K, the algebra of compact operators on an infinite dimensional separable Hilbert space. Say H. Well, this is an exercise, but nevertheless, let me say slightly more explicitly how this isomorphism is constructed. Actually, this is one of the most important examples of C-star algebraic inductive limits. So more explicitly, we choose a countable of normal basis, say En, in our space, an orthonormal basis. And for every n, let Pn denote the projection of H onto the linear span of the first n elements of the basis, E1 to En. And let An denote the, by the way, a sub-exercise here is to show that Pn is an approximate identity in the algebra of compact operators in K. So let's now denote by n the following subalgebra: Pn, K, Pn. So another sub-exercise is to show that An is a C-star subalgebra, the C-star subalgebra of the algebra of compact operators. And moreover, it is isomorphic to the matrix algebra Mn, so there exist isomorphisms between An and the matrix algebra Mn, such that the isomorphisms are compatible with the inclusion maps here and here. So from this diagram, we can easily deduce that the C-star inductive limit of Mn is isomorphic to the C-star inductive limit of An, that is, to the closure of their union. And since Pn is an approximate identity in K, it follows that this union is dense in K. So in summary, the C-star inductive limit is isomorphic to K. Let's now look at another example of a C-star inductive limit. Example exercise 2. Let's denote by D the following diagonal map from C to C plus C. So it takes Z to the pair Z, Z. The diagonal inclusion of C to C plus C. So clearly this is a star algebra homomorphism. And now we take the following inductive sequence. So here we have D. Then we take D plus D, which acts from C2 to C4. Then D to the power 4, which acts to C to the power 8, and so on. So this is an inductive sequence of C-star algebras. So we can form the inductive limit. The exercise is to prove that the C-star inductive limit of this sequence is isomorphic to the algebra of continuous functions on the Cantor set. And the algebraic inductive limit is a suitable dense subalgebra in CFK. Another example, example 3, illustrates the difference between algebraic and C-star algebraic inductive limits. So let AN denote the algebra of continuous functions on the interval from -1 over n to 1 over n. So for every n we have the restriction map from AN to AN plus 1. This is the restriction map. So we obtain an inductive sequence of C-star algebras. Let's also denote by Bn the ideal in AN, which consists of all functions vanishing at 0. So if we take the algebraic inductive limit of our sequence AN, then it's easily seen that this is nothing but the algebra of germs of continuous functions at 0. The algebra of germs of continuous functions at 0. That is, equivalence classes of continuous functions defined in neighborhoods of 0, and two equivalence classes are the same if two such functions are equivalent if they agree on a smaller neighborhood of 0 containing the intersection of their domains. Let's denote this algebra by A. And similarly, the algebraic inductive limit of Bn consists of those germs F in A which vanish at 0. So a simple exercise is to show that both A and B, let's denote it by B, A and B are infinite dimensional star algebras. What happens if you take the inductive limit in the category of C-star algebras? Here the situation is totally different. Exercise 2 show that the C-star inductive limit of the sequence AN is one-dimensional. And the C-star inductive limit of the sequence Bn is 0. So this example shows that in general, if we work with not necessarily injective inductive sequences, in the general case, the algebraic inductive limit and the C-star inductive limit can be very different. Well, more examples of inductive systems of C-star algebras and of their inductive limits will be contained in the respective exercise sheet. Our next goal is to prove, so let's now come back to K-theory. Our next goal will be to prove the continuity of the functor K0. The continuity of K0. So suppose we have an inductive system of C-star algebras, AI, together with connected maps phi ij. Inductive system of C-star algebras. Let's apply the K0 functor. So it is a functor. So clearly, after we apply this functor, we get an inductive system of abelian groups. It is an inductive system of abelian groups. And if we now form the C-star inductive limit of our C-star algebra system, that's denoted by A, and the canonical maps will be denoted by phi I. So let's now observe that K0A becomes a cone over this system. K0 of A together with the maps phi I star is an inductive cone. Over the system K0 of AI. Just by the commutativity of the suitable diagram. So it is an inductive cone, and by the universal property of the inductive limit, we see that we have a natural homomorphism from the inductive limit of these groups to K0 of A. Hence, there exists a unique homomorphism from the inductive limit of K0f of AI to K0 of A, that's denoted by alpha, which is a homomorphism of inductive cones. That is a unique homomorphism such that the following diagram commutes. This arrow, let's denote this arrow by A alpha I, such that this diagram commutes for every I. And here alpha I is the canonical map from this group to the inductive limit of these groups. I claim, and this is our main theorem for today, the continuity of K0. I claim that alpha is an isomorphism. So in some sense, we see that K0 commutes with inductive limits. The proof will be divided into several lemmas. Lemmas 1, 2, and 3 will enable us to reduce everything to the unital case. Lemma 1, which is an exercise at the same time. I claim that the C-star inductive limit of the unitizations of our algebras, AI plus, is naturally isomorphic to the unitization of the C-star inductive limit of AI. So inductive limits commute with the unitizations. There are many different ways of proving this. You can either use the explicit construction of the inductive limit, or you can use, if you like, you can use the universal property of the unitization and of the inductive limit. So both approaches lead to a rather simple solution. Lemma 2, which is also a simple algebraic exercise. Actually, this is a very well-known property of the inductive limit. The inductive limit, say in the category of abelian groups, is an exact functor. This is the exactness of the inductive limit. So suppose we have an exact sequence, an exact sequence of the following form of inductive systems of abelian groups. Suppose we have an exact sequence of inductive systems of abelian groups. Well, when I say that our sequence is exact, I mean that it is exact at every level. That is, the respective sequence AI, BI, CI is exact for every I. I claim that if we take the inductive limits, then we still get an exact sequence. This is a rather simple exercise. It's very easy to deduce this result from the explicit construction of the inductive limit of abelian groups. Lemma 3 is a reduction of our theorem to the unital case. If our theorem is true for all inductive systems of unital C-star algebras, and unital star homomorphisms, then it is true for all inductive systems. For all inductive systems of C-star algebras. The proof is a simple combination of lemmas 1 and 2. First of all, we take any I in our index in our set I, and we look at the respective exact sequence, which appears in the definition of K0 for non-unital algebras. So by definition of K0 for non-unital algebras, the following sequence is exact. For every I. We can now take the inductive limit of the sequence, and lemma 2 shows that the respective sequence of the following form is still exact. Well, of course, the inductive limit of the constant system consisting of the same abelian group of integers is the same group of integers. So this sequence is exact. Let's now look at the middle term of the sequence. So here we have a system of unital C-star algebras and unital star homomorphisms. So by assumption, this limit is isomorphic to K0 of the C-star inductive limit of the unitizations AI plus. And this holds by assumption. Let's denote this isomorphism by alpha, say tilde. This is the same alpha, but applied to the unitizations of our algebras. And also, by lemma 1, we can identify this inductive limit with the unitization of the inductive limit of the algebras AI. K0 of the unitization of the inductive limit. Let's now draw a similar sequence for this unital algebra. So here we have Z and K0 of the inductive limit of the algebras AI. Again, this sequence is exact just by the definition of K0 for non-unital algebras. Here we have the identity map, and it's easy to observe the diagram. There's the diagram commutes. This is a little sub-exercise to show that the diagram commutes. So if we restrict this isomorphism to this subgroup, we get alpha. So the sequences are exact. This is an isomorphism, this is an isomorphism. This implies that alpha is also an isomorphism. And this completes the proof of lemma 3. So as a result, we have reduced everything to the unital case, to the case of unital C star algebras and unital star homomorphisms. So from now on, we assume that everything is unital. We assume from now on that AI are unital, phi ij are also unital. And of course, in this case, the inductive limit A is also a unital algebra. A is unital, and the canonical maps phi I from AI to A are also unital. Well, this falls from the construction. If we remember the construction of the inductive limit, we form the inductive limit in the category of algebras. So if we believe that this is true in the category of all star algebras, then we take the quotient, the suitable quotient of the algebraic inductive limit, which is unital. The quotient of a unital algebra is unital, and the completion of a unital algebra is unital. Morphisms are also, of course. But in that case, the algebras are unital, but the phi ij are not unital. So there is no contradiction here. It's essential that the morphisms phi ij are also unital. Not only the algebras, but also the morphisms are unital. Okay. Lemma 4. This is a technical result about invertible elements. So if A is an element of one of the algebras AI, then I claim that the image of this element is invertible in A, if and only if the image of the same element is invertible in Aij for some index j greater than or equal to I. Well, first of all, let's observe that the right to left implication is clear. This is clear because we work with an inductive cone, and because phi I of A can be written as phi j applied to phi ij of A. And so if this one is invertible, then this one is also invertible. So any unital homomorphism takes invertible elements to invertible elements. So what is interesting here is to prove the left to right implication. Well, this element is invertible. So the first step is to approximate the inverse of this element by the image of a suitable element in one of our sister algebras Aj. So for every positive epsilon, we can find an index j and an element b in Aj such that the image of B, phi j of B, is close to the inverse element, to the inverse of this one. This is smaller than epsilon. This is because the union of the images of phi I the union is dense in A. If I now multiply this by phi I of A, we see that phi I of A, phi j of B minus 1 by this multiplicativity, this is less than epsilon times the norm of phi I of A. And if epsilon is small enough, this can be so we choose epsilon such that this is less than 1. If epsilon is small enough. So these are elements in A. A little problem with these elements is that they come from different algebras. So this one comes from AI, and this one comes from AJ. But we can push them forward to make them belong to the common algebra AK. So let's introduce some auxiliary notation for every k greater than or equal to I. Let AK denote the image of A in AK, or of A into A in AK. If we now choose K such that K is bigger than I and J, let's now choose K such that K is greater than or equal to I and greater than or equal to J, then we have phi I of A is equal to phi K of AK, just by the commutativity of this suitable diagram. Similarly, phi J of B is equal to phi K of BK. And if we substitute it here, we see that phi K applied to AK BK minus 1 is less than 1. So now this element comes from the algebra AK. And if we now recall the construction of this norm, so this is the norm on the inductive limit. So by construction of this norm is equal to the infimum of AL BL minus 1, where L is greater than or equal to K. And therefore, since this is the infimum, we can always find L greater than or equal to K such that AL BL minus 1 is less than 1. Why is it useful? This is useful because this automatically implies that this element is invertible. This is one of the most basic properties of one algebras, that an element which is close to the identity is invertible. So this implies that ALBL is invertible in AL. And if we multiply it by the inverse element on the right, we deduce that AL is right invertible. AL is right invertible in AL. Well, we want to make it invertible, but we can now repeat the same procedure by multiplying this inequality on the right. So here we multiplied it on the left by phi I of A. We can multiply it on the right. So these two will be interchanged. And a similar argument shows that we can find an element, say R, greater than or equal to K, such that BR AR minus 1 is less than 1, and so AR is left invertible in AR. I'm sorry about this notation. So left invertible would be better to denote by L and right invertible by R, but I hope there is no problem here. So this one is left invertible, this one is right invertible. The final step is to choose an index which is bigger both than L and R. So choose S greater than or equal to L and S greater than or equal to R, and we deduce that AS, so it is the image of this element and at the same time of this element in AS. AS is the left and right invertible in AS. But of course, an element which is both left and right invertible is invertible. So AS is invertible. And this is exactly what we wanted to show. So we found an index S such that the image of A under this respective connected map is invertible. This completes the proof of lemma 4. Okay, I see it's time to finish. Let me only just briefly explain the plan of the end of our proof. So just to understand where we are going to. So the next step, lemma 5, will be to show that the unitary group of A can be represented as the closure of the union of the images of the unitary groups of AI. Again, the right to left inclusion is more or less clear. So this one is contained in this one because phi I is a unital homomorphism, so it takes unitary elements to unitary elements. And of course, the unitary group is closed. So the closure of this union is contained in this. So what is essential here is the opposite inclusion, that is any unitary element in A can be approximated by the image of a suitable unitary element in the respective algebra AI. And the same is true for projections. Lemma 6, the set of projections in A equals the closure of the union of the images of projections in AI. This is quite convenient and closely related to K-theory, because if you remember that K-theory is defined in terms of projections in matrix algebras, and one of possible ways of defining an equivalence relations between projections is the unitary equivalence. And so these lemmas will enable us to reduce properties of projections and equivalences of projections in A to the respective properties in the algebras AI. And moreover, at this point I'll skip one more auxiliary step, which shows that in a similar way we can approximate pairs of unitary equivalent projections. So if you have two unitarily equivalent projections in A, then this pair can be approximated by the image of a suitable pair of unitarily equivalent projections in AI. So these two equalities are compatible in this way. And also, so this is true for A, but K-theory is defined in terms of projections in matrix algebras. But fortunately, the matrix algebra over the inductive limit is easily seen to be isomorphic to the inductive limit of matrix algebras. So finally, if we combine these three properties, this will enable us to prove that K0 of the C-star inductive limit is isomorphic to the inductive limit of K0 of AI. So this is briefly, this is our plan. Okay, So that's all for today. At the next lecture, we finish the proof of continuity of K0. Then, as a corollary, deduce that the functor K0 is stable. That is, if we multiply sister algebra by the algebra of compact operators, then K0 will be the same. This is also a very useful technical property of K0. And then discuss the functor K1 for system algebras, which is actually closely related to K0. Okay. Also a few words about our plans. So on the 2nd of May and on the 9th of May we have holidays. So we will have to skip the lectures. So our next lecture will be on the 16th of May. And formally it will be the last one, the last obligatory lecture for those of you who are either the fourth year bachelor students or the 2nd year master students. As for the continuation, this is up to you. So if you like, we can continue, for example, up until the end of May and discuss relation between K0 and K1 and finish by proving the Bott periodicity theorem, which is a very useful computational tool in K theory. But you will have some time to think about it until the next lecture. Okay, thank you.